Okay, so I have started recording. All right. So basically, okay. So in the last class, last Friday, we were discussing about crystal structure, and we have almost finished the discussion on crystal structure, crystal planes, crystal directions. So today we'll move to the next chapter. So before that, there is only few things left. I just want to remind you. Um, so we talked about planes and direction, and we also discussed that 100 plane is best suitable for transistor fabrication. So because the defect density is much lower in 100 plane compared to 110 and 111, right? Okay, so here because the wafers we get from an ingot, right? So so in the right hand side here, if you see, so this is a crystal ingot. So this is grown by Czochralski method. So then we slice it and get our wafers. Basically, um, when you slice it, you also give a pointer, like, so basically there is a notch or there is a flat to indicate a direction. Otherwise it's very difficult to know the crystal direction from the crystal wafer. So so what is generally done is you have, so uh, if you have a wafer, so what you have given, so basically there is either there is a flat in this, so the flat, or there is a notch, right? So one of these two. So the flat, it indicates that this direction is 110, right? So basically this is the 110 direction. So if you see how this is defined, so if this is the wafer here, if this is my wafer here, so right, so this is my wafer. So here you see this flat indicates 110 direction, right? Okay. So when you take the wafer, so transistors are normally horizontal or vertical to the notch. When you do a layout and put the layout on the, means basically you design the mask, the transistors are placed horizontal or vertical to the notch, right? So so if you look at this transistor here, right? So this is a MOS transistor. So we have source, drain, gate. So source is in the left side, drain is in the right side, and the electrons usually flow from source to drain, and the flow of electrons is in 110 direction, right? So this direction here, this direction here, so this is 110, right? um, so also if you see, if I come back to here, if this direction is 110, the direction perpendicular to this is also 110, right? So we have seen in the, find out the direction, right? So this direction is 110, this direction is also, sorry, this direction is also 110, right? So direction perpendicular to 110 is 110, right? So basically, even if you put your transistors in this way, vertical, right? So electrons are flowing vertically, means from here to here, right? So here also electrons are flowing in 110 direction, right? So basically it is preferred because the electron mobility is higher on 100 surface and 110 direction, right? Okay, so now if I have 100 plane, right? So this is the wafer plane, one wafer surface 100, and we know this is, here it is 110, right? Here this is 110 direction. This direction is also 110, right? So what is this direction? So if let's say you did your layout in such a that your transistors are not horizontal or vertical, you have just at an angle of 45-degree, right? Let's say you put your transistor at an angle of 45-degree in the layout, right? So what is this direction? What will be this direction? You know, this direction is 110 notch. Okay. Anybody? What is the direction perpendicular? Sorry, at a 45-degree to 110.
100.
Anybody? Okay, so somebody spoke, right? Okay, so what is the direction? Okay, so Sarda, what will be the direction which is 45 degrees to 110?
100, sir.
Yeah, it will be 100. 100 is correct. You could even see from here, right? Okay, so what is this direction here, right? So if I take a different color here, so what is this direction? So this direction is, this red one is 11110 direction, right? Right? I think we discussed this, right? This is 110 direction, right? So this direction here, this will be 100, right? So basically, if you put a transistor a 45-degree tilt, right? So when you tilt a transistor in 45-degree, so electrons will not flow in 110 direction; they will go in 100 directions, right? So this is 10. So this is the thing. I mean, see, uh, you do different tricks to improve the performance of the transistor, right? So basically, what do you mean by the performance of the transistor? So we are mostly interested in current because this is a voltage control, I mean, voltage control current source, right? If you give voltage, you'll get current, right, in a transistor, right? So basically, for a fixed voltage, we need to have high current, right? And current depends on charge into velocity. Since velocity is coming from the mobility of electrons. So mobility depends on which direction the electrons are flowing, right? So whether which crystallographic direction they are moving. So so basically, people do a lot of tricks, right? So they also change the layout. They also means you could tilt your layout so that your transistor uh, will have electrons will have better mobility, so the current will be higher, right? So you should know these things. Okay. Um, I mean, we also have discussed this, and there are a lot of papers on mobility planes and directions, and this is very well established. Is the electron mobility is highest in 100 substrate. The in 100 substrate direction doesn't have much effect, right? The electron mobility on 100 substrate is about half of that on 100, right? So on 110, the electron mobility is the lowest, right? Um, okay, so the whole mobility, other means in contrary to electron mobility, the whole mobility is higher on 110 substrate compare I mean and the lowest on 100. So this is totally opposite to electron mobility. So this part we have discussed. So that's the reason you see in your transistors. So let's say if you go back to this direction, uh, uh, this picture here. So here, if this is a PMOS transistor, right? So if this is a PMOS transistor, so the PMOS transistor, the whole mobility on 100 plane is lowest, right? So that's the reason compare because we cannot have see basically the whole mobility is higher on 110 plane, right? But since we are starting with 100 plane, so whole mobility is always lower than the electron mobility, right? And basically in modern transistors, so the whole mobility is almost 1.5 times lower than electron mobility. But in FinFETs, when you go to very advanced transistors like FinFETs or nanosheet FETs, I mean, let's say FinFETs, the FinFETs, the whole mobility is comparable to electron mobility because the electrons are flowing in different way there, right? So we'll discuss this when we'll come to transistor, MOS transistor. But to give a um, I mean, so to give a glimpse of what we're talking about. So basically, in FinFET, right? So FinFET is a 3D structure, right? Basically, you see, uh, so uh, uh, so so FinFET is a 3D structure. So this is your 100 plane, but this plane here, right? This plane here, right? Let me write this plane here, right? So this is my transistor, right? So basically the silicon is my fin and the gate is all around the silicon here, right? So the electrons are flowing. So this is my source here, right? So this is the source and this side is drain. So electrons are going from source to drain in this direction, right? So but you see, so if this plane here, this plane here, this plane here, let me, this plane here is 100. What is this plane which is colored green, right? Which is that plane? If the top plane is 100, that is where the wafers, means we have our wafer surface is 100, right? So if this plane is 100, the side planes, the perpendicular plane is always 110, right? So this plane is 110, right? So since the electrons are moving in both the, means both the planes, 100 as well as 110, right? And we know that electron mobility is lower in 110 plane, right? So we are not getting much advantage in FinFET in terms of electron mobility. But hole mobility, you see, holes are also flowing in 110 planes because we have a 110 plane in FinFET, right? On addition to the 100 plane, right? So that's the reason the hole mobility is higher in FinFETs or FinFETs compared to electron. I mean, in some cases, the hole mobility is higher higher than electron in case of FinFET. But mostly, if you see the universal curve or IV characteristic of a PMOS FinFET and NMOS N FinFET or P FinFET, so their mobility, their drive current is equal, right? Mostly the whole mobility is almost same as the electron mobility. That's the reason when you do the design. So, so basically, if you have done the digital design course, you know that you size the transistor based on the mobility, right? So since the mobilities are equal, so your sizes of both NMOS and PMOS transistors will be equal.
Sir,
Yes,
sir,
Paul.
I have a question. Sir, you said that the top plane is 100 plane and the green one is 110, right?
Hmm.
But sir, when we were studying about these planes, we saw that for a cube,
Yeah, I got your
all the
point. So you're
surface,
telling that, okay.
the
So,
diagonal
but
was
the way
110.
this is diced, right? So you see here, right? See how do you dice it, right? So basically, this is your 100 plane, right? So when you're talking about that other plane, the way you dice matters, right? So the perpendicular plane is this plane, right?
Oh, yes, sir.
So this plane is which plane?
It is 110.
Yeah. So generally you are right. The 100 planes are on another 100 plane is perpendicular to each other. But the way you have done in this means the way you have diced your wafer, you have cut your wafers, right? So basically your 110 plane, because you have defined the 100 direction and the flat direction, right? Right. So the 110 plane will be perpendicular to this surface, right? So the here the yellow is the surface. Yellow surface is your 100 plane, and 110 will be perpendicular, right? Okay. So anyway, so we'll get back to this thing when we'll discuss about FinFET. But this is just for your information. So the electron and hole mobility will depend on crystallographic planes and crystallographic direction, right? Okay. Okay. So then we'll means um, we'll go to our next uh, part of the course. So now we know that means basically we are interested in silicon, so we'll mostly concentrate on silicon. So we know that silicon is a diamond cubic crystal, right? The silicon is a diamond cubic crystal, and it has a lattice constant of 5.4 angstrom, right? Right. And so this is a unit cell of a silicon crystal. The unit cell means you can take this unit cell and repeat this unit cell to get your 3D crystal, right? So and when I'm talking about lattice constant, so this is your lattice constant. This is the distance between two atoms, so which is 5.4 angstrom, right? And we know that in a unit cell, there are 8 atoms, 8 silicon atoms per unit cell, right? And we know that, so there are 5.10 to 22 atoms per centimeter cube, right? So these are things we know from the crystal unit cell. So we have 5 into 10 to 22 atoms per centimeter cube. So let's say, you see, for example, I have 5 into 10 to 22 atoms per centimeter cube. Let's say I take a semiconductor cube, a silicon cube, which is 1 micrometer into 1 micrometer into 1 micrometer, right? If I take this silicon, then the number of atoms will be, I could calculate easily, right? Number of atoms will be 10 to minus 12. So this is 5 into 10 to 10 atoms, right? So basically, in 1 cubic meter of silicon crystal, 1 cubic meter volume, so there are 5 into 10 to 10 atoms, right? So there are a lot of atoms, right? So, okay. So now let's say when if I reduce the dimensions of the that cube, the number of atoms will reduce, right? Anyway, okay. So now I also told you that the properties of the semiconductor is derived from the unit cell, right? So what do you mean by property of a semiconductor? So basically, yeah, I have just taken this table from a book. So if you see, this is silicon. So this is when you talk about the property of the semiconductor, we are mostly interested in these properties, right? So uh, atomic weight, right, which we have discussed, right? So silicon has an atomic mass of 28, right? Atoms per centimeter cube. So this part we discussed. Density also discussed. Crystal structure is diamond cubic. Lattice constant 5.43. So then the important thing is energy gap, because we are talking about semiconductors. So semiconductors are defined by a property is called band gap, right, or energy band gap, right? So the band gap of silicon is 1.12 electron volt. Their dielectric constant 11.7, and there are also a couple of other things which we'll discuss, like intrinsic carrier concentration, carrier mobility, effective density of states, breakdown field, melting point. So all those properties that I have listed here, that has been listed here, right? So uh, this totally depends on how the crystal structure of silicon, right? Right? That's the reason we started with the crystal structure. And not only crystal structure, if you know the unit cell of the silicon, right, you could get all those properties from by simulating the unit cell, right? So if you take the unit cell of, you know, the unit cell of silicon, then if you do ab initio simulation like density functional theory, you could get all those properties, right? Like band gap, mobility, intrinsic carrier concentration, all of those things, right? All of these things, right? So but when we are using semiconductor, silicon as a, means in our device, because silicon as a semiconductor, right? Because we are using silicon as a semiconductor. So the first properties that we talk about is conductivity, right? So conductivity, um, right? So conductivity or resistivity. So it's the same. Is the same thing, right? Resistivity is nothing but the opposite. One by resistivity is conductivity, right? So this is very important, and because semiconductor is the only material where we could change the conductivity or resistivity by changing the doping, right? That we know, right? But doping is an external thing, right? But semiconductor by itself has some certain conductivity, and that is directly dependent on the band gap, right? So so this conductivity part, right? The conductivity resistivity, right? So this is nothing but how many electrons and holes we have in a semiconductors, right? So if you take a silicon, So what is the intrinsic carrier concentration? What are the electrons and hole concentration in a typical in a semiconductor? So that defines the conductivity resistivity, right? But when you talk about number of electrons and number of holes, so this depends on two things. I mean, is a very important uh, parameter which is called density of states, right? So basically, we'll discuss about this. We have in Saturday's lecture, Mohit also talked about density of states or energy states. So the density of states is very important to for the conductivity of a semiconductor. So one is density of states, and second we'll also discuss something called the Fermi-Dirac statistics, because these two things will give you how many the number of electrons and number of holes in the semiconductor. So how many of you have heard about density of states? Can you tell me what is density of states? Because I assume that you might have done it in your basic semiconductor course, right? So what is density of states? Anybody? How do you define density of states? Bhavesh, any idea? Density of states?
So number of states where the electron can go in the conduction band.
But how can this be density? What do you mean by density of states? Nishant?
Sir.
Okay. Anybody else? Shruti?
So number of states per
Yeah,
unit area
Monica.
per unit volume.
Yeah, number of electronic states per unit volume per unit energy. Basically, this is per centimeter cube per electron volt, right? Density of states, the unit of density of states, if you remember. So this is per centimeter cube per electron volt, right? So, so density of states tell you number of electronic states per unit volume per unit energy. What do you mean by electronic states? Electronic states is a energy states where an electron can go and stay, right, or sit, right? So basically, this is a energy state, right? So, uh, so to give an example means to give an example, let's say if you want to find the number of students in a classroom, right? So if you find the number of students in a classroom, right? So how do you find the number of students in classroom? So basically you look at the classroom, how many chairs are there in the classroom, right? So so that how many chairs in the classroom, this is nothing but the density of states, right? How many energy states available, right? So that is the how many chairs are there in the classroom. If there are 40 chairs, right? So then that means the maximum students that could be in that room is 40, right? That's why density of states uh, is a very important parameter for the carrier concentration, right? So higher the density of states, higher the higher is, I mean the carrier concentration will be higher, right? Electron hole concentration will be higher, right? Then okay, so even if we have 40 chairs, it's not necessary that all the chairs will be filled by the students, right? So the probability of a chair to be filled is nothing but the statistics, right? So at a certain point of time, let's say if you take a chair, if you know that okay, the probability that chair will be filled is half, right? So means if you see every day that okay, means you see for 10 to 20 days, and you see that okay, the probability is only half, right? So that means the number of number of students is nothing but number of chairs into probability. So 40 into half, right? 20, right? So basically, so this is the so that's the reason. I mean, here, so we'll see in this course also, to find the number of electrons and number of holes, we have to first know the density of states. Then then we'll multiply this by the Fermi statistics, right? So okay, so then the density of states, if I come to density of states, this is nothing but number of energy states or number of energy states per unit volume per unit energy, right? So this is the density of states, right? So this density of states is mostly defined by quantum mechanics, and means Mohit has discussed on Saturday the basics of quantum mechanics. So if I go to, means basically if I it means if you recall some of the discussions that happened on Saturday, so so he talked about EK diagram, right? Energy momentum diagram. So he started with a free particle, right? So basically he started with a free particle. The free particle is like a electron, or let's say a particle, a electron, which is not influenced by any potential energy, right? So so it's a free, it is not not means it is moving in a area which is free of any potential energy, right? So that is a free particle. And uh, we discussed about this free particle, and from there we derived the EK relationship. And uh, just to um, for your information, I'll just write down. So basically, so if you write the Schrodinger's equation, right? Right. So basically, if you write down the Schrodinger's equation, 1D Schrodinger's equation, this is nothing but minus h bar square by 2m d square psi by dx square plus u psi equal to e psi, right? And here u is the potential energy, right? So for a free particle, u is 0, right? So so we have written this as 2me by h bar square psi equal to 0, right? Then we have solved this, right? So so if you solve, the solution of this is a e to the power ikx plus b e to the minus ikx, or also you could write in terms of sign, right? So basically, if you solve this, in the free particle behaves like a standing wave, right? So it could move in any direction, right? Positive x direction or negative x direction, right? And the momentum, right? So so basically, if this is a standing wave, but the standing wave we could write in this way, right? I kx minus omega t, right? And here k is nothing but my wave vector, or k equal to 2 pi by lambda, right? So from this analogy, so you could write this k is nothing but, in this case, k is root over 2me by h bar square, and e is nothing but h bar square k square by 2m. And if you plot this, right, this is the EK diagram. So k is nothing but the momentum here. So this k is the crystal momentum, right? So basically, or in the free particle, this is the momentum. So so h bar k is the momentum, right? So your momentum p here is h bar k, right? This is your momentum, right? Momentum of the particle, right? So if you plot it, right, if you do E as a function of k, right, then you will get something like this, right? So that means the particle, so so here, so E, let me write down again, E equal to h bar square by 2m. Anyway, so this is the mass of the particle, m. H bar is the Planck's constant. So so basically, so the energy of the particle can be defined from this curve here. So the right? So the energy of the free particle is nothing but it depends on the momentum, right? So basically, and so so the energy, so basically here you see the free particle can take any energy, right? So it can be here, here, means the possibility it can be here, right? So these are the energy states of that electron, right? So basically, if the electron here, so if you take, means if the electron is free, that means it is moving in an area, it's not influenced by any potential energy, then it could take any energy state, right? So basically these points here are the uh, energies where the electron can be, and electron can be anywhere, right? So so basically the free particle can have any energy depending on the momentum. So basically if you look at the states, so these so these are the states, right? So basically it can be continuous states, right? So basically these are the energy states, right? And the energy state is continuous for a free particle, right? So for a free particle you could have infinite energy states, right? So basically the free particle can be anywhere, right? So I think this part is clear, or is this part clear from the last discussion, Saturday's discussion, or anybody has any doubt here? Because I'm going it little bit, means I'm doing it little bit fast, because we have already spent 2.5 hours on Saturday on it. So any doubt from anybody? Okay. Nishant, Om, Sarda, Monica, Aditya, Shruti.
नहीं सर ये
No,
पार्ट
sir.
क्लियर है
No,
सर.
sir.
Yeah, this part is clear, right? And Swati, how is it for you? Are you following me today?
Yes, sir. A little. I will go through the lectures and then I will see again, sir. A little bit I'm getting.
All right. Okay. Okay. Fine. So now, if I take this particle, and so now this particle, the particle is free, right? So when it particle is free, that means it could take any energy state, right? So it has infinite number of energy states, right? But if I take this particle and confine it, right? So when I confine it, let's say I confine it. So I'll put it in a potential well, right? Right. So if my electron is that potential well, that means this is not free anymore. So this is confined in this potential well, and right. So let's say this is 0 potential energy, and this is some ux, right, or u, right. Okay. So now if the electron is not free anymore, it is confined, right? So here, then if you solve the Schrodinger's equation, which we have solved on Monday, right? So if you solve, right, so you could take this equation again. U psi equal to E psi, right? So this is your Schrodinger's equation. So if it is an infinite potential well, so basically it's a the electron is in a potential well, but it is an infinite potential well. That means if U is called infinite, right? So there is there is 0 possibility that electron can go out, right? Because if it is an infinite potential well, the electron cannot go out. So the probability of finding the electron in this part and this part is absolutely 0, right? If it's an infinite potential well, there is no possibility that electron can be found in other part, right? So electron is only electron is means can only be found in this potential well. So but in this potential well, your U is 0, right? So if you solve this, your psi x, right, if this is the x direction, and let's say this is 0 and this is a, so the width of the potential well is a. So then if you solve this, right, so you will have something like a sine kx plus b cos kx, right? So in this way, right, where k here is 2me by h bar square, right? So, so now you could put the boundary conditions. You could put the boundary conditions. So basically, so we know that at x equal to 0, psi x equal to 0, because x equal to 0, your psi x equal to 0, because the electron cannot go out. So at the boundary, the probability of finding the electron is also 0 because it has to be continuous, right? The psi is continuous, right? So, so you do that, then b equal to 0, then x equal to a, also psi x equal to 0, right? So if you do that, then 0 equal to a sine ka, right? And ka is nothing but plus minus n pi, right? So your k is nothing but n pi by a. So then if you take your energy, which is h bar square k square by m 2m, right? Right. So it will have h bar square 2m n square pi square by a square, right? But here you see the energy is not continuous because we have here a n term, right? And this n value can be 0, 1, 2, 3, right? So what happens? So if you take an electron and confine it in a potential well, and this is an infinite potential well, so the energy is not continuous, right? Because you have the n term. If n equal to 0, the energy is 0, right? If n equal to 1, the energy is h square pi square by 2m square, right? So basically your energy is not continuous, it is discretized, right? That means you could find electrons in a specific energy only, right? And this is for n equal to 1, n equal to 2, n equal to 3, like this. So here you see the, in this case, in the other case, your energy state is continuous. Electrons can be any energy, right? Because it's a free particle, right? But when you confine it, it has discrete energy states, right? And these are called energy states, right? These are called energy states, right? So if I come back to a density of states, so this is, if I take, if you see, so here the things are discretized. So if you take the density of states per electron volt per centimeter cube, if you see the density of states decreases when for a free particle, the density of states is infinite, right? So you can, the electrons can be in n number of energy because it can be at any energy. But for a confined particle, right? So number of energy states is discretized, number of energy states is less, right? So so basically, when I'm talking about a, so basically this is a scenario of an atom also, right? In an atom, if you take a atom, right? So let's say if I take a hydrogen atom, right? Hydrogen atom has one electron, right? So but that electron is inside that atom, right? This is, the electron is also confined, right? So basically, so when you talk about atom, the electrons, it is confined because it's not free, right? So basically, if I take an atom, the electron is, there is a potential energy, right, in atom. And from where this potential energy is coming, because there is one atom, also there is a nucleus, so there is an attractive force between, means that nucleus is positively charged, right? So the electron is influenced by that potential energy, right? And means if you see, I think Mohit has also discussed this in last in the Saturday's class. So so the potential energy, so this is nothing but I mean, so the potential energy will be minus q square by 4 pi epsilon 0 r. So if you draw in an atom here, so basically your potential energy looks like this, right? So if this is, the atom is here, right? So the potential energy, I mean, so when you go very close to atom, the potential energy is very high, right? If you go far from the atom, right, the potential energy decreases. This is, this somehow it looks like this, right? So and electron inside this potential well, right? so it has discrete number of states, right? As we solve, it could have a discrete number of, states, right? And means I think all of you might have done in solve the hydrogen atom, right? And hydrogen atom is the most simple atom, right? It has only one electron, right? So basically, so when you talk, when you uh, talk about atom, so inside that, so atom is nothing but like a potential well, so it has a certain number of states, right? And the electron can only assume one of these states, right? And so these states are called quantum states or energy states, right? And right. um, okay, so I think I'll is it clear to everybody?
Yes, sir.
Okay, so I'll just I have just go to one of the means I take some slides from my one of my lecture. So here you see, this is how the atomic orbitals are defined, right? So basically, if you see, um, so the atomic orbitals are typically categorized by NLMS quantum numbers, right? And these are these different states, right? So basically, uh, you have this principal quantum number, which is means energy is nothing but minus 13.6 by n square electron volt. This is for a hydrogen atom, right? So NL is the azimuthal quantum number, M is the magnetic quantum number, and S is the spin quantum number. So based on that, uh, you know the atomic orbitals, right? So um, so the first energy states, so n equal to 1, there can be maximum of 2 electrons, because any energy states, uh, you could have two, means we could say basically the energy states we can have 2 electrons, so because both 2 electrons with 2 different spins, right? So n equal to 1, I have 2 electrons, so that is the s orbital. When n equal to 2, I have 2 electrons. At the same time, we have also by orbital angular momentum, we have 2 orbital angular momentum, right? Then we have the magnetic quantum number. So based on those things, so when n equal to 2, which is means we can have s and p orbital, and that could carry maximum of 8 electron. So and for n equal to 3, so we have spd orbitals, right? And we can have maximum of, right, so 18 electrons in the n equal to 3, right? So basically, this is how the atomic orbitals are defined, right? And this is means all of you might have done this. So the point here is, so if you look at the means for a silicon, right? So when you're talking about silicon, right? So the silicon has a atomic number of 14, right? So we write it as 284, right? So basically, so there are at n equal to 1, so there are 2 electrons, and these 2 electrons are moving to different spins, right? So these 2 electrons have 2 different spins. So then I have n equal to 2, I have 8 electrons, and n equal to 3, which could carry maximum of how much, right? Maximum of 18, I have only 4 electrons, right? And these 4 electrons, we call it valence electrons, because these are at the outermost orbit, and these electrons can be easily removed from the atom by applying some energy. So that's the reason they're called the valence electrons, right? So we have 4 valence electrons, and since they are in the outermost orbit, so they also participate in the bonding, right? When I'm talking about silicon crystal, so each silicon is bonded with 4 neighboring silicons, right? Because they form covalent bonding, right? So we have 4 electrons, right? So let's say a silicon has 4 valence electrons, right? So these 4 valence electrons, uh, so they bond with 4 different silicons, right? Right. So basically, they bond with 4 different silicons, right? So these valence electrons are responsible for this covalent bonding, right? So the point here is, even if when you talk about silicon, right? When you talk about, I'll go to my, right? So when you talk about silicon here, let me look at the, yeah. Here you see each silicon, means silicon is bonded to 4 neighboring atoms, right? So in this case, if you look at this silicon is bonded to this one, and this one, and another one here, right? So each silicon is bonded to 4 neighboring silicon atoms. But if you look at the atom itself, right? So let's say if you look at the individual atom, right? So the individual atom, um, so the individual atom, so basically you could, right? So the individual atom has discretized energy states, right? So so n equal to 1, n equal to 2, n equal to 3. So discretized energy states, and here I have 2 electrons, right? So here I have 8 electrons. Anyway, right? So 8 electrons, and here I have 4 electrons, right? So so these are discretized energy states, right? So actually when you're talking about the states, right? So these are the energy states, right? These are the states where, sorry, so these are the states where you could have electrons, right? So when you talk about energy states, um so these are the energy states, right? So inside the atom is a confined system, right? So that's why the states are quantized, right? So if you take this electron, and means if you take this electron out of the atom, then the electron will be free, right? So when the electron is free, then it will have n number of energies. It could have any energy, right? Okay. So now, but in a crystal, right? So here I have a single atom, but in a crystal I have I have more number of atoms, right? So let's say if I, okay, so if I talk, right? So yeah, here, right? So basically, so if I talk of a single atom, right? Single atom. So we have some discrete states here, right? So these are the states where the electrons, you could find electrons. Now, since in a solid crystal, we are talking about, means let's say this is a 1D crystal, right? So we do not have 1D crystal in the nature, but let's assume this is a 1D crystal. So so I have, so and this is my unit cell, right? And I could take this unit cell and repeat, right? So I'll get a 1D crystal, right? So, and A is the lattice constant, right? So now if I bring all these atoms, means if I put a second atom, so the potential energy of the first atom will interfere with the potential energy of the second atom, right? Similarly, if I have a third atom, so this potential energy of the third atom, right, will also interfere with the potential energy of second and first atom, right? So basically, if you bring atoms together, the if you're so basically your potential energy, so if you plot, let's say this is the distance x, right? So I have let's say few atoms. So if you see in this direction of x, the potential energy will be in this way, right? So and uh, so the distribution of this potential energy will depend on the value of a, right? So if your a is far apart, right? So if a is very high, then maybe the potential energies will not interfere, right? So right, but if a is very close to each other, right, so then they will interfere, right? Then I'll have something like this, right? I have a modified potential energy, right? So depending on the lattice constant, so you will have you'll have different potential energies, right? So basically when you define U, so as means discussed by Mohit, right? So um, when you solve the Schrodinger's equation, right, the input to the Schrodinger equation is the potential energy, right? So here the input, so if you want to solve, okay, now with this number of atoms, so what is the possible number of energy states, what is the possible energy I could have for the electrons? So basically then the input to your when if you want to solve Schrodinger equation, the input is ux, and ux will take this shape like this, right right. Then you have to solve, put this ux in your Schrodinger equation, and the solve for E, the total energy, right? So but this will be very complex, right? So there are a lot of assumptions taken, and I think the first one is the chronic penny model. Means we will not go in detail the chronic penny model. So I think the people, I mean the students who are registered for the lab course, you'll have one assignment on the to solve the chronic penny model. So basically uh, here, so you could approximate, right? So let's say this is my my potential landscape, potential right, ux, but ux I could approximate this by by something like this, right? So basically uh, uh, right, so um so this so here these are the atoms here, right. So I could because I could make it a simple ux, because here this is a complex function, because your potential energy is changing by 1 by r, right? But I could make it simpler, so like a potential well kind of things. So this is the Cronin Penny model. So so this first approximation is done by Cronin and Penny. So basically then this is much easier, because here I mean so I'll not go in detail, but the point is uh, as discussed by Mohit also in the last class, so every atom, so let's say, has particular energy states, right, but when you bring them together, right, when they bring them together, these energy states will mix, right, and they will form bands, right? So I'll not go in detail, but I think when you bring these atoms together, so basically every atom has discrete energy states, right? So when you bring them together, then we'll have bands, right? So basically if you see um, a deep very close to the atom, so we'll have still the cells, we have still the states, right, discrete energy states, right? But if you go away from the atoms, so you'll slowly have different bands, right? So these are called energy bands, right? Energy bands, right? So these energy bands has a lot of energy states, right? So the energy bands has a lot of energy states, right? Because uh, so right, so here this here, so I have only one state, one energy state, but here this part here, so I'll have few energy states very close to each other, so that's why they are called bands, right? The energy bands, right. So basically when we're talking about the bands, so basically the electrons which means basically the electrons which will um, take part in the conduction, or which will define the conductivity or resistivity of the semiconductor, they are the valence electrons, right? And these valence electrons are available in the outermost band, and this band we call the valence band, right? So basically uh, the valence band, right, the valence band, so this is nothing but, so let me define. So let's say I have um, band, right? So so this is the band 1, and this is my energy band 2, and this is the my energy band 3, right? So at 0 degree Kelvin, right? So valence band is defined that the lowermost band which is filled at 0 degree Kelvin, right? So at absolute zero temperature, if this band is filled, right, and there are no electrons in band 2 and 3, right, then this is defined as valence band, right? This is defined by the valence band, and the next band to the valence band is nothing but the conduction band, right? This next band to the valence band is nothing but the conduction band, right? So this is how the valence band is defined, and once you know the valence band, you could the next band is the conduction band, right? In this case, let's say at absolute zero temperature, if this band is, we could find electrons only in this band, will not find any electrons in this band, right? Then this is defined as the valence band, and this is defined as the conduction. This is how the valence band, conduction bands are defined, right? So the valence band and conduction band, the energy of the valence and conduction band, that depends also on the atom itself, right? So for a silicon, the valence band conduction band is different from the germanium valence band and conduction band, right? So so if you could see, so the position of valence band and conduction band will depend on the lattice constant, right? On the lattice constant A, right? So if you move them closer and closer, you will see that your bands will split more and more, right? So you will have bands which will be separated by more distance, right? Okay, and also it will depend on the number of electrons, number of, I mean, so the atomic number of the uh, of the atoms, your material, right? So silicon has an atomic number of 14, but germanium has a higher atomic number. That means it has more number of electrons. So so it could so their valence band will be different than the valence band of silicon, right? So just the last, I think I could means here means so here you could see, right? So so if you look at this part, these are the isolated atoms, right? If you separate the atomic means the lattice constant or atomic separation, if you reduce the separation between two atoms, and if you go on reducing, then this energy states will split, right? Because two atoms are coming very close to each other. That means electrons from these atoms can also assume some energy state in the different atom, right? So they are mixing, right? So since one electron cannot means one electron can only one energy state, so the split, right? So the states split, right? So basically, you see the outermost states will split first, right? And so so they will form bands. So you see then we'll have the energy bands, and from the energy bands we could find which one is the valence band, conduction, and depending on the electrons, availability of electrons at absolute zero temperature, right? So so you see means the band gap again, right? Band gap, right? So when I talk about band gap or the energy gap, uh, so this is also depend on the uh, atomic number of the semiconductor material, right? So you see so the carbon, silicon, germanium, and tin, there are all group 4 elements, right? So periodic table, they are in the same group, right? So carbons have the lowest atomic number, silicon has the highest means more atomic number than carbon, then germanium, then tin. But when you look at the band gap, right? So band gap here you see carbon is a very high band gap, right? 5.47 in the crystalline form. The silicon has 1.12, germanium has 0.616, tin has the lowest band gap, right? So you see the atomic number here has also influence on the band gap, but when you look at the silicon, germanium, the lattice constants are almost same, right? We have discussed in the last class. The silicon, germanium lattice constants are almost same, but the band gap is different because germanium has a lot of electrons compared to silicon, right? So atomic number of germanium is higher than silicon, right? So right, similarly
Sir,
yeah,
what is
Bhavesh.
direct and indirect band
Yeah,
gap.
I'll come to that point, right? I'll come to that point and maybe in the next class. Uh, uh, so right, similarly, so we have different semiconductors. So 3 5 semiconductors like gallium arsenide. So gallium arsenide, indium arsenide, indium atom, indium. So these are all uh, right, zinc blend structures. Gallium arsenide, indium antimonide. Gallium nitride is a woodside structure, woodside crystal. So basically, depending on the lattice constant of their unit cell or lattice constant of those crystals, and uh, the atomic number of the atoms involved, right? So the band gap is defined, and you see the um, uh, gallium arsenide has 1.42 electron volt band gap. Gallium nitride has a higher band gap, 3.35. But there are like indium arsenide has a low band gap. Indium antimonide has a even lower band gap. So, so this is how the band gap of the different semiconductors are defined, and uh, you could get the band gap as I told you several times if you know the unit cell and unit cell of each crystal, and you know the atoms, right? So when you talk about unit cell means you have atoms arranged, means atoms are arranged, but also you have to take, okay, if this is a silicon atom, right? So when you look at the unit cell, the silicon unit cell and German unit cell will look different, but they will not have same band gap because because germanium atom is different than silicon. That's the reason they will have different band gap, right? So if you take the unit cell with the atom itself, then you give it to the simulator, like we have ab initio simulators like DFT. So this will give you the EK diagram, right? So EK diagram, the energy momentum diagram, that will give you the bands, right? So from the energy momentum diagram, you could find out the band gap, right? So EK diagram, then so basically the DFT, the density functional theory or ab initio simulation, all are done at the absolute zero temperature, right? So since they are done at absolute zero temperature simulations, then it is very easy to find the valence band, because valence band is nothing but the band, the lowest band where you can find electrons. Then if you know if you find the valence band, then the band on top of that is the conduction band. Then you find the energy difference between valence band and conduction band. Then you find the band gap. Right? This is how the band gap uh, is calculated in different semiconductors. Right? Okay, I think I should stop here. Any questions? I understand there will be a lot of questions, but I have some time we could uh, discuss.
Sir, can you please put the previous slide once? Sir, in this, it is being shown, sir, are those two states at the bottom, are they also forbidden?
No. States are not forbidden, right? So as you say, basically, okay. So when I talk about, let's say, we'll go to this potential well, infinite potential well. So electrons, let's say we could have only these energy states, right? Right. So, but any states, there will be no states between these two energy states, right? Right. So this is called the forbidden gap, right? Right. So that means we have one energy states here. The next energy state is here, and the gap is forbidden. That means you cannot have any energy states between these two states, right?
Yes, sir.
So forbidden is they are not, means they are not energy states. This is the energy between two energy states. They are forbidden, means we cannot have energy, and electrons cannot be there, right? Or there is no energy states between.